The next interesting circuit is known as a multiplexer. Okay, so short form is you usually call it a mux. Okay, mux and a demux and so on, right? So what we are basically trying to do, by the way, in the decoder, if you look at what we are trying to do is, you can even look at this, why is it called a decoder? Because the information of the address is encoded in 3 bits and we are decoding what that actual information is. We are translating that encoded address and decoding it into a physical location or an address that we are going to go and reach out to. So that's why it's called a decoder. Okay. Now the next circuit that that is very commonly used and very useful is the multiplexer. Okay. Now what is the multiplexer? Again, let's look at it from the black box perspective. Okay. Here I have, let's say, 4 inputs: I0, I1, I2, I3, right? And the multiplexer's job is to select one of the 4 inputs and translate and just connect it to the output. Okay, in some sense it's like, I have a switch that is actually choosing which input should go to that particular output, right? So it's like on this train track, right? You have basically the train that can come, okay, and it could turn and go this way, or it could go straight. How is that done? That is done using one of those levers where you either connect the track and cause the thing to go this way, or you cause it to go that way. So the input is just going out that way, or the input is going out the other way, right? So this is one actually no, I think that would be more apt for a demultiplexer. So I'll keep that analogy for the demultiplexer for later. Okay. So in any case, what I have here is it's like having 4 different taps. Okay, and I'm going to choose one of these taps to fill water into my tank. Right, the 4 sources could be different. One could be corporation water, one could be the bore well, one could be a well that I have in my house, one could be some rainwater harvested source that I have, and I'm going to choose which of these taps will fill my tank. And I'm also going to make the assumption that only one of these will be open at a given time, right? So if you were to do such an implementation, what is the logic circuit that is actually needed? Okay, so again it's a 4:1 mux. Okay, I'm looking at this as a 4:1 mux. Let's look at the truth table as usual. So I have I0, I1, I2, I3. Okay, now to select between 4 inputs, I need at least 2 other select signals because there are 4 of them. That's why you will see even the multiplexer is always, the number of inputs is basically in powers of 2. Okay, the decoder, the output was in powers of 2. Here we are saying the inputs, the number of inputs will go in powers of 2. 4:1 multiplexer, 8:1 multiplexer, 16:1, 32:1 and so on. Okay, so I have 4 inputs and I obviously need 2 other select lines, S1 and S0. These are my 2 select lines, S1, S0. Okay, and again I have 0, 0, 0, 1, 1, 0, 1, 1. Okay, and now I am not going to worry about this combination actually. Okay, I am going to write this truth table slightly different because you already see for just a 4:1 multiplexer, what do I have here? I have 6 input combinations. So if I wanted to write this truth table out fully, I would have to write 64 combinations, which is just too complex. So I'm not going to write all this. Okay, I'll represent this truth table slightly differently. I have one output Y. If S1, S0 is 0, 0, then I want I0 to be the thing. So what does that mean? It means if I0 is 0, Y should be 0. If I0 is 1, Y should be 1. or as long as S1 and S0 happen to be 0, 0, whatever input you give on Y or on I0 should simply appear at the output Y. Okay. So this is what I want here. This will be I1, I2 and I3. Okay. So now this is very interesting, because what it basically says is that I need to first um, generate some minterm, right? So if I were to write this carefully, Y will simply be I0 into M0 plus I1 into M1 plus I2 into M2 plus I3 into M3. Okay. These are M0, M1, M2, M3 are the min terms that I wanted. So how would I go ahead and implement this again? It's very straightforward. We just do the same thing that we did for the decoder. Generate true and complement. Okay, for the select signals. S1, S0. Now M0 is going to be, okay. So again, this could be implemented in different ways. I could first generate M0 using a 2-input AND gate if I wish, right. So this is what I have, okay. And I could then take this output and AND it with I0, okay. Now likewise I could do, so this is going to give me M0, I3. So I will just take this output and this output, okay, right, and I will get the 4 min terms that I wanted for this expression. So let me call this as some x0, x1, x2 and x3. So out here I'll get x0, I'll get x3, then eventually I need to put them through an OR gate, because I have the sum of products that I want. From here you will get x1, then x2, and eventually I'll get my multiplexer output Y out here. Okay, this is Y mux. Okay, so this is sort of a reasonably straightforward implementation of the multiplexer, right? So if you look at the it's also important for you to be able to plot the outputs as a function of time. Okay, for example, I may have S0 and S1 going through such a cycle. Okay, um, let me just partition this time into 4. Okay, S0 and S1 could be like this. S1, S0, this is your I0, okay, my input, which could be something like this, okay, and then you could have certain outputs like this, okay. I1 could be, again, you could have very arbitrary activity happening here, and this output will be like, let's say the input changed like this, okay. Then my output Y of this multiplexer, if S0 and S1 were 0, 0, so this is 0, 0, 0, 1, 1, 0, 1, 1, right. As long as S0, S1 and S0 are 0, 0, the output will just follow I0. So therefore, Y will simply follow I0 here, okay. When it comes to the next, when the input select signal switches to 1, 0, S1 is 1 and S0 is 0, then the output will simply follow I1. So it will ignore what is happening on the other inputs and simply appear like this, right. And I am not showing for the case of I2 and I3, that is also a very straightforward extension, but you should be able to plot this time function as well, depending on the inputs, because ultimately the multiplexer will be used in practice for something like this, right. Certain this is a digital multiplexer. You also have analog multiplexers where the output will just follow the analog signal as it is, right. But ultimately the logic that implements this is going to be very similar at the fundamental level, right. uh, so with that, I'll stop the discussion on the decoder and the multiplexer, and we will then look at certain other gates that will help simplify these implementations for us going forward.